All right, in this video, we're looking at probability, two types of probability. One of them for events involving and the other one is a concept called conditional probability, okay? Now, we had looked at all the different types of probability already on that problem that had a Venn diagram, okay? So, now we're just going back, and this video is focusing on just those ones at the bottom of that page, those three questions at the bottom of the page that had the odd numbers and the multiples of 3. So this problem's similar to that. This one, though, only had the numbers 1 through 9. It didn't include the 10 that we had on that other sheet. So it sounds like the same problem, but this one only has the numbers 1 through 9. All right, so here what we're going to be doing is we're going to be looking at the following following questions. We're going to be looking for the probability of A and B and the probability of B given A. So this notation right here, this means the probability. This is the probability of, I'm just going to abbreviate it, probability of B given A, okay? And B in this case is being a multiple of 3. And A in this case is given that the numbers are odd, okay? Sorry, it's hard to write when on this tablet, so my writing's a little messier. Okay. All right, now, so this first one's looking at conditional probability. And so it's like the probability of some event happening with the knowledge that some other event has happened or is happening or will happening. Really, what time, whether it was before, after, or during, does not matter. I like to think of it as some other event has already happened, is the way that makes sense to me. This is called conditional probability, okay? All right, and this is the conditional probability. This is the notation for it. So the probability of B given that A has happened, okay? So let's go through the problems that you see here. All right, so this one's has these two events. So A is the event of being odd. So we're really talking about this subset of the sample space, just 1, 3, 5, 7, or 9. All right, then B is the event of being a multiple of 3, which means you have to be divisible by 3, so that would be the number 3, 6, or 9, okay? So if we wanted the probability of B, that means the probability of being a multiple of 3, because there are just 3 numbers that are a multiple of 3, we would put 3 over 9, because we just have the numbers from 1 through 9. So that's going to turn out to be a third, okay? All right, now for the probability of A and B, we're using the and like we did back in chapter 2. It means that we have to be both a multiple of 3 and also odd. So what we're going to be doing is looking at these two sets and looking for what's in the intersection of those two sets. Okay, so that would be 2 over 9. Okay, and that doesn't simplify. All right, so this one is just the number of elements in set B divided by the number of elements in the sample space. This one is the number of elements in A intersected with B divided by the number of elements in the sample space. All right, now for this last one, I want you to first just think of it intuitively. Okay. For this last one, the idea is that we're starting with all 9 of these numbers, right? So we have all 9 of these numbers in our sample space. If we want to know the probability of being a multiple of 3 given we're odd, it's like we're starting with all 9 of these numbers, okay? But then event A happens, given that, see, it's probability B given that A has happened. A was being odd, so it's like, okay, so now we're not really dealing with all of that. We're down to just these, okay? And now we want the probability of being a multiple of 3 from that set, and that would just be these two, and our answer to this one would be just 2, but it wouldn't be over 9, it'd be over those 5 odd numbers. So this, given that statement, given that we're odd, that is what makes the denominator. That's what gives you out of those 5 elements. All right, so what we're really doing here to get that, the formula that you'll see for the conditional probability formula really just does that. Okay, so I like to think about my sample space was all of these, but then I know A has happened, right? So that means I'm now down to this group. And then when I do the probability of being a multiple of 3 out of that, I'm not really making my denominator the whole sample space. My denominator is those 5, okay? Now, the formula for finding conditional probability of B given A is actually the one that we're using. We're really doing this concept right here. We're looking at, we could think of it like the number of elements that are in both A and B at the same time. Okay, so the number of elements in both A and B at the same time, which are these two. But then the denominator needs to be the number of elements in set A, in that event that's after the vertical line. Okay. Now these other two formulas are true. These are correct. This is also the idea of what we're doing, but they would turn out on that previous problem, they would turn out looking a little different. Like if you were thinking about that, the probability of finding B given A using these formulas, these first two, what you would do is look for the probability of A and B, which is 2/9, and then divide that by the probability of being set A, which I didn't ask, I wish I had. Probability of being set A would be 5/9, okay? And then you have to simplify that, and when you do simplify that, that becomes just 2/5, right? So we're just going directly to this, okay? Taking the number of elements in A intersected with B and dividing it by the number of elements in set A. And so that approach is more what we're doing. All right, so let's look at another problem and let me get you to understand what these sets really are. So this is given a family with 2 children, okay? So family with 2 children. So the idea there would have been for the first child, it could have been a boy or a girl. Second child could be a boy or a girl. So that means you could have boy, 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 girl, girl, boy, or girl, girl, okay? That's the sample space because we're dealing with this experiment of having a family with 2 kids. So that's the sample space. Now, we want the probability that both are boys. That would be BB. But then we have a given that at least one is a boy. So we have the probability that both are boys given at least one is a boy. Okay? So they're calling this set B, both being boys. See, there's that BB. And they're calling this A. So we're really looking for the probability of both being boys given that at least one is. So think about at least one being a boy. So out of that sample space, if we had at least one being a boy, that means we could have GB, BG, or BB. That's where this came from. This is at least one boy. Okay, and then this is both boys. Both boys. Okay, so we want the probability that both are boys given that at least one is. So that means what we did is we started with our sample space, the whole sample space. This is how I like to think about it. But given that at least one is a boy meant then we were down to this many outcomes, this many possible results. And then I want to know that the likelihood we're going to have both boys, assuming we're down to this, that would wind up being one outcome out of 3. Okay. Now we could have used the formula up here, this formula right here. We could have done the probability of the being in the intersection of these two sets. Okay. And that would be, 1 probability of being in the intersection of these two sets would have been 1 out of 4. So the chance that you'd be in both of those would be 1 out of these 4. And then the probability of being set A would be 3 out of 4. And then when you simplify that, you'd get 1/3. Okay? So the way I'm actually doing it is not so much using those formulas, but using this one. But as I think about that one, I'm thinking about starting out, clean that up a little bit, starting out with my sample space. Then this is the first event that I'm thinking about it like, okay, so then that event happens, which makes me now only have these 3 outcomes. And then I want the likelihood of being both boys out of that, which would be 1 out of 3. Okay? So we're really just restricting our sample space. When we have this, we're restricting our sample space to whatever that is. All right, now let's take just a moment to talk about independent events. You won't really have a question about what makes an event independent, but whether or not 2 events are independent will affect how you answer your probability questions later. And I think there's a homework question like this, so I wanted to go ahead and mention it. So independent events are events where if one of them happens, it doesn't have an effect on the probability that the other one will. So that means if the probability of B given that A has happened would be the same as the probability of B, that whether A happened or not doesn't affect your answer. And it also would be true the other way. If we looked at the probability of A given B, we'd get the same thing as just doing the probability of A, that whether B happens or not, it doesn't affect the outcome of the probability of A. So some examples that are just clearly independent would be flipping a coin and then rolling a die. Okay, whether you get heads or tails on the coin has no impact on whether when you roll the die you get an even number or not. So that's independent. All right, another one is like if you selected a ball from an urn, that's like a vase, and you looked at the color of it and then replaced it back into that ball. If the first ball turned out to be blue, and the other event is the second ball is blue, those would be independent because we put the ball back in. So if we're replacing the ball, all right, that's the key to keeping things independent. Okay. However, if that ball was not replaced before the second ball was selected, then getting a ball the first time through, if it didn't go back in to that urn, that vase, then that's going to change what the probability would be for getting blue on the second one. All right, so here, what we're really trying to do on this question is just determine ultimately whether A and B are independent or not. All right, I find it a little odd to ask that question when you're not really doing two separate events. I usually like to think of it more in terms of two separate events happening, one and then I do another. You'll see what I mean later when we do problems, but we're going to just work this as is. All right, so here we're drawing a card from a standard 52 card deck. One event is the card is an ace. The other event is that the card is red. Okay. So the probability of the card being an ace would be 4, since there's 4 aces out of 52, which is 1 out of 13. Probability a card is red would be 26 out of 52, because there's 2 red suits. 26 of the cards out of 52, that would be 1/2. So the probability of being red, that's the 26 out of 52 or the 1/2. Now this is saying find the probability of being red. Okay, probability of being, this is red. Sorry, it keeps on doing that. Given that we have aces. Okay, probability of red given we have aces. So there, what I'm thinking about is my 52 cards to start with overall. But now the first thing that happens is I'm down to my aces. So I'm thinking about those 4 aces. And out of those 4 aces, there are 2 red ones. And it turns out being 1/2. So to be independent, we'd want the probability of B given A to equal the probability of just B. Okay. And so the probability of B given A was 1/2, and the probability of just being B was 1/2. So yes, they're independent because we wound up seeing that it didn't affect the probability. We got the same thing, whether A happened or not. Okay. All right, and then I got to wondering if I probably should have tested also, what would be the probability of A given B? And what's the probability of just A? So the probability of A is 1/13. I got to thinking about the probability of A given B. I maybe should have tested that. And the probability of A given B means I started out with my 52 cards, but now I'm down to 26 cards. Okay. And then out of those 26 red cards, I just have 2 aces, and that would wind up being 1/13. So either way you do it, whichever order you do it in, you're getting the same. You're getting that this is not affected by B happening, and this right here was not affected by A happening. So A and B are independent. A and B are independent. Okay.